we're going to show you some pictures in a moment. Yeah, there we go. Anyway, I'm just delighted to be back in Almeria. I came here in 2008 because of John Beckman and his invitation to participate in the Jornadas Astronómicas. And I'm sorry I can't speak this in Spanish, but I'm glad to see you're all here because I have some secrets to tell you about, and I don't have all the answers. That's why they're mysteries. So here on the screen, I am showing you here, the Canadian Space Agency. It took about 20,000 people to do. Oh, and I did use this microphone. Okay, it took about 20,000 people for that project to be built. It was launched on Christmas morning in 2021, and it's been now in space for about 3.5 years. We're getting wonderful results. It's basically a perfect observatory, just as good as we hoped it would be. And every astronomer in the world can use it. You write us a proposal, you send it in once a year, and we'll read your proposal. And we have now a method called anonymous review, so we don't know who you are when we read your proposal. So a faculty member, a student here at the university, can send us a proposal to use the Webb telescope. So even if you're in China, you can still do that. And the data are going to be public after a little while. Let me tell you about some of the mysteries that I'm going to tell you about while I'm waiting for the slides to come back. We have now almost a century since quantum mechanics was developed. Quantum mechanics tells us that what we have been thinking about as particles are actually waves. And when it was first recognized that this is true, it was a very big surprise because we knew things have a particle nature, and nevertheless, even 200 years ago, we knew about this. Okay, it's coming. Anyway, that's one of the big mysteries. Coming back. Okay. Excellent. So, anyway, here we have the James Webb Space Telescope. You see the great golden hexagon there. It is 6.5 meters across. It's bigger than most telescopes here on Earth. It's a little bigger than the Calar Alto telescope. It's 3.5 meters. And it is not nearly as large as the telescopes we are building. As you probably know, Europe is building a telescope in Chile called the Extremely Large Telescope. It will be 39 meters in diameter, so 6 times as large as this beautiful telescope. Anyway, this one is in outer space, and it is put there for a particular reason, to observe infrared light, which we cannot observe from the Earth. So it's, as we mentioned, it's available to everyone. Let's see if I can push the button here. So why are we doing all these things? So many of us have these questions. Where did we come from? So of course our short answer is we got it from Darwin. We are descended from ancestors here on Earth. But where did that happen? How did that happen? How did life occur here on Earth? That's a big mystery. What does it mean to say we? Obviously we are part of an immense process. Each one of our bodies is made out of about 30 trillion cells, approximately 30 trillion microbes. We have about 86 billion neurons, each of which connected to something like 1,000 other neurons. So an extraordinarily complicated thing, and that's only for each one of us, and there are about 8 billion of us, to say nothing of all the other living creatures and plants here on Earth. So we're all part of this combined whole, and that's a bigger mystery than I can explain. So what is our cosmic history? Astronomers can tell you how it happened. How did the atoms produce an Earth? And also we have some hope eventually of telling you a little bit about whether we are alone. Are there other living things on other planets? And if so, where are they? Sort of basic question everyone seems to have is, well, can I do what it says in the science fiction stories that I read when I was younger? And the answer seems to be mostly no. I'm sorry, we cannot go out of the solar system with anything that we can imagine today. We can send some probes out of the solar system, but if they go somewhere, it'll take a long time. So, however, astronomers, we can imagine everything, and so we can tell you the stories, and I'll try to tell you some of them. So our world is extremely complex, and the history of every single thing is special. So each of us is different. Each planet in the solar system is different. Each planet around another star is different. Physics and biology combine at this point. They look a lot similar. So there's a lovely book called A World Beyond Physics, which I recommend to you, by Stuart Kauffman. And in particular, he does the calculation to say that no, although the universe is infinite, no, there is not another you just like you somewhere else. There might be other beings, but they're not like you. So that's interesting. We know about genetics on opportunity, and philosophers and scientists have been asking about free will for a long time. So I think there's less than we think there is, and yet we must have it. We talk to each other as though we are responsible citizens, and we can make promises and we can be counted on. So that's, I think, a part of that discussion, but I'm not going to be able to answer that question. So, unsolved mysteries that I want to tell you about a little bit. Dark matter, dark energy, and cosmic inflation. These are some things that astronomers work on a lot. There seems to be more stuff in the universe than you can measure with a telescope. You can find out where all the stars are, you can find out where all the gaseous material is in between the stars, and that's not everything. There's something going on that produces extra gravity, and we've known about it since about 1935, but we don't really understand it. We've never been able to measure any of it in a laboratory, and so it's going to be a mystery for a while. It might be a permanent mystery. We astronomers are going to measure more about it, but we may never be able to answer that mystery. Dark energy is something that makes the universe accelerate. It expands faster and faster and faster every year. And we certainly did not predict it. We don't understand it. And it might or might not be simple. What we can do as astronomers is to measure the rate of change, to see whether it's the constant that Einstein told us about, or maybe something else. So what else about things do we not know? Well, if you've been following the science, you know about particles that they discover at the Hadron Collider. And they found the Higgs boson a few years ago, and the Nobel Prize was given for that and for the prediction that it exists. We don't know if that's the end. That might be the end of everything they can find with that equipment, and might not. And it might be we have to build more equipment to find even smaller, more energetic objects. So we don't really know. Then there's the mystery of quantum mechanics. I'll show you a little bit more about that. We don't know if the universe is deterministic or chaotic. Deterministic means if you knew where all the particles were and all the waves were at the very beginning, you would know what they were going to, or in principle, you would know what would do next. So when this idea was recognized after Isaac Newton gave us the laws of motion from force equals mass times acceleration, philosophers are immediately very upset, because what does that mean about free will? Are we really creatures of God with spirit, or are atoms making us do it? So that was a philosophical question, and it still is a philosophical question, even with quantum mechanics. There's something called the Hubble tension. We have multiple ways of measuring the rate of expansion of the universe, and they're not giving the same answer. So they're pretty close agreement, but not quite. So maybe there's another mysterious force out there for us to discover. So John Beckman and I have both been working on the cosmic microwave background radiation for decades. And there's something a little bit fishy going on. There's a little bit of extra radiation that's not unknown, not understood. We may or may not have the right measurement, so we have to go measure again. That's among many puzzles that just an observations that's not understood. We built the Webb telescope partly to find out about the early universe, and we were wrong about what we saw. We've seen things, so probably what we're seeing is correct, but what we thought we were going to see was different. A recent result that's quite puzzling is that galaxies spin more in one direction than another, at least nearby, and this was a huge surprise, and I don't know if it's true, but it's so surprising that I should be skeptical, but the people that measured it think they're correct. So this is a typical kind of puzzle in science. We have a puzzle, we have an observation, we don't understand it, and we all have to work on it to see if it's still there in 5 or 10 years. Lots of other things in this list, but I'm going to skip over the rest of them because we'll come back and show you more. This is a little story about me. This is where I grew up. This is a farm in far northern New Jersey. It's about 80 miles northwest of New York City, and it's extremely rural, very, very quiet. Trees, grass, woods, cows, barns, and a research facility for Rutgers University. That's where my dad was studying cows, and where I started to begin to learn science. So I didn't have any idea of what would happen next, but I grew up to become a scientist and be able to come to talk to you. That's a complete surprise. So going back a little bit in time, though, I want to show you how we found out about the expanding universe. In 1929, Edwin Hubble drew us this graph. Each little dot on the graph represents a galaxy. On the vertical direction, how fast is it going away from us? On the horizontal direction, how far away did he think these galaxies are? And the obvious thing is there's a trend here, that the farther away they are, the faster they're going away from us. So how did this happen? Well, if you imagine they were all started together, then you can divide the distance by the speed and get the age of the universe. Extremely simple calculation. Divide distance by speed, get the age. So he got the wrong answer, but all the same, it was a start. So we now call this the Hubble-Lemaitre law, because Georges Lemaitre was a Catholic priest who had a PhD in math and physics, I think, from MIT, and he applied Einstein's equations, and he said this should be true. And he had some of the data, but he wasn't pushing himself forward, so he didn't get a lot of credit for a while. Now we understand that he really was a brilliant man, and he should get some of the credit for this too. So, and he wasn't even the first to do some of these calculations. Friedman had done that some years before. At any rate, Einstein was completely amazed by this. He didn't even quite believe it. He was sure this must be incorrect until somebody showed him that he'd made a mistake in his calculations. Oops. Anyway, so now we know the universe is expanding. Different distant galaxies are going away from us. So we talk about the origin of the universe, but that is as though you could step outside the universe and picture it. But no, we can't step outside the universe to picture it. But we can say the universe is expanding now. Distant objects are running away from us. There is no sign of an edge. That means the universe could be infinite in extent. The easiest to guess is there's just no, it keeps on going and going and going. But you can't see that far, so you would never be able to prove it. So what we can do is imagine running the expansion of the movie backwards until everything is compressed and compressed. So we can't get all the way back to the zero of time, because then as our calculations go, we just don't know what to do. We can't calculate something with extremely high temperatures and densities, but we can begin to imagine. So there's something we've invented called inflation that would say, well, have an idea of what came very early and it caused the expansion. So it would explain a lot of what we've seen, and it might be true, but there's many details to be worked out. So it's a bit of a mystery. So I don't know if we're ever going to find out the rest of that mystery, but at any rate, the concept is the part of the universe that you can see now, that's 13.8 billion years in every direction, was compressed into a volume as big as a small golf ball. So that's the story we have, and it's the best one we have, but it might not be true. So I'll talk a little bit about quantum mechanics. So people talk in the news all the time about how quantum mechanics is very mysterious. Well, it is sort of, but maybe it's not as mysterious as people say. So a long time ago, people thought, well, surely light is little particles passing through space. Isaac Newton thought it would be particles. Other people said, well, what if it's a wave? And then they proved that it was a wave also. So a wave will bend around corners, just like ocean waves will bend around corners. So that was a huge surprise. What's a quantum field? It's you describe it by a number at each place in space and time. And so now this describes a wave, numbers everywhere in space and time. And we've discovered that these waves can have mass and charge, and they can even describe something that spins. So then we have lots of equations for this, and many Nobel Prizes have been given for discovering the details of these equations. So now we're pretty darn sure that this is the right story. So quantum mechanics really works, but what we call particles are actually little packets of waves, concentrated waves moving as though they were particles. So that's a bit of a puzzle for people, because we just didn't like that. If you call a thing a particle, you imagine that it's a point, but they never are points. They're always packets of waves. So there are a handful of them that we know about. Gravity, electricity, electromagnetism, and two kinds of nuclear forces are described by these quantum waves. And it's been an extremely successful catalog. We have this huge catalog of these things, and that's what all the Nobel Prizes are about. And then we get to the end of my page here, and it says dark matter and dark energy. And we don't know what those are. We don't know if they're quantum fields. We don't know if there is a defect in our story of gravity. Maybe the gravity that Einstein gave us is wrong in some way. So still hunting for this answer to those two at the end. Maybe they're not quantum fields. At any rate, a puzzle. So anyway, these various different kinds of things combine together to make everything you can see. So if somebody asks you, is quantum mechanics is important? Well, it is. Every atomic nucleus is governed by quantum mechanics. Every atom is governed by quantum mechanics. Every molecule is quantum mechanics. So everything you see is the result of quantum mechanics. So when you send your students off to learn quantum mechanics, you should understand they're sending them off to learn everything about the world. Everything is quantum mechanics, especially, the tricky one at the end here is living material. So it's clearly governed by quantum mechanics. Now we don't know the details, and that's not anyway, to be determined. A mystery for biologists, really, to understand how does living material function. So I'm not going to tell you that because I don't know. So anyway, the puzzle about quantum mechanics is these waves are real, but people talk about them as though they're probability waves, but actually I think they're just real. And so you can't measure a wave like that without bothering it. So that's what we have a puzzle we call measurement. If I try to measure a wave, it's not the same wave anymore because I bothered it. So this is confused physicists for generations now, and I think maybe it's actually quite simple. So what the physicists say is, well, I don't know, but just calculate. And maybe that's the right thing. So now I want to come back to the universe as a whole. This is the project called the Cosmic Background Explorer Satellite, which was built to measure the early universe. So to tell the truth, it grew out of a failed thesis project. I was a graduate student in Berkeley. I had tried to make a balloon payload to measure this cosmic radiation just about a little while after John Beckman and his team were doing that from England. And anyway, my thesis project did not work right. I ended up getting a job for NASA to try some other kind of physics, some other kind of astronomy. And then NASA said, oh, we want proposals for new satellite missions. And I said, okay, let's try this. And my boss said, okay, we know who to call. We'll call up our friends. We'll write a thin proposal. It was very thin, just about 20 or 30 pages. And basically it says, we have an idea. And so a couple of years later, NASA said, okay, it's a good enough idea. We want to start working on it. So 15 years after the first sketch, it went up into space, and this is what we imagine it looks like. So we did two things with it that really surprised people. Number one is we measured the spectrum of the heat of the early universe. Is it really the remnant of the Big Bang, as we call it? And the answer is yes, it fits exactly. And number two, is it the same in every direction? And this is our map that says, no, it's not. So this is a rather fuzzy map, and it's been superseded by two much better maps, one with a NASA satellite and one of the European satellites. So anyway, the map says, not only is it not the same temperature every place in the early universe, there's slight density variations. Stephen Hawking saw this map. He said it was the most important scientific discovery of the century, if not of all time. I thought, well, that's really sweet of you to say that. So why would it be so important? Well, number one, the spots represent density variations as well as temperature. So that means some areas of the universe had more gravity than others, and those areas that had more gravity, more mass, were able to stop the expansion of the material, and it would fall back in to make clouds of galaxies or even individual galaxies. So we are here because there are spots in this map. And if there weren't any, we think the universe would still be featureless, would have nothing in it at all, just no stars, no galaxies. So we're here because of the spots. Number two, or for the rest of it, is exciting for a scientist because it tells us about dark matter and dark energy and maybe eventually quantum gravity, which we don't understand either. So that was a prediction. Well, put it this way, when we started off to propose this observatory, we had no prediction at all to test. People often say, well, you're trying to build an observatory to test a theory. Well, actually, our objective was to get some data, because there was no theory at that time. By the time we launched it, there was a theory, and it sort of matched. Anyway, now we have what we call a standard model of cosmology, and it fits the data very well, except for a few things. So anyway, so now we say we know what the early universe was like. What would happen next? How did the galaxies grow from that? I told you the story. Is it right? So just a few months after that satellite was launched, the Hubble Space Telescope was launched. And here it is. It's 35 years old already, and it's still working very well because astronauts have been up to visit it 5 times to fix it and improve it. So as soon as we got it working, we saw that it was out of focus, and that was a huge disaster for NASA, but the end result was we figured out what the mistake was, and we sent up astronauts with new equipment to fix it. So they did not change the big mirror, they changed what happens after the mirror. So anyway, they got it fixed, and then astronomers said, that's beautiful, and we still have a question about the early universe. Please build us another even more powerful telescope that can see farther back in time, farther out in space. And that's this one. This is the James Webb Space Telescope. And by the way, who is James Webb? He was the second administrator of NASA. He was the man who went to Jack Kennedy with a plan to go to the moon. And just as a little bit of perspective, 8 years later, people walked on the moon. So here, we can't even have a decision in 8 years anymore, but they did that. To me, it's a miracle of human organization, as well as engineering progress, and I'm sorry to say that it required a Cold War to propel that. But at any rate, we did that, and so I think it was good that we could name a telescope for this amazing person who made it happen. Anyway, who is the telescope? It's a joint project, as I mentioned. It has 4 instruments inside that basically take pictures of the sky. They take images, and they also spread out the light of each star or galaxy into a spectrum, so you can say how bright is it at each different wavelength. And that lets us do chemistry and calculate motions of things. So, a picture's worth 1,000 words, as they say. For an astronomer, a spectrum is worth 1,000 pictures. So it's very, very valuable, and we spend much of the time of this observatory taking spectra. So anyway, the telescope is cold. I'm going to show you a little bit about it, but the temperature of the telescope is about 40 Kelvin, 40 degrees above absolute zero, so that it does not emit infrared light, because we want to measure infrared light. So why observe infrared? Well, here are a few examples. We want to look inside dust clouds where stars are born or die. This is a dust cloud with a star in it, and you can just barely see that there's a star in the center. And this is a picture taken with the Hubble. Hubble also has an infrared camera, and it when you look at the longer infrared wavelengths, you can see through the dust cloud. So this is because light's a wave. When light passes a dust grain, it can either bend around it or bounce off it. If the light wavelength is short, it'll bounce. If it wavelength is long, it'll go around. So able to see inside dust clouds, to see stars inside. Second reason is to see things that are too cold to emit their own visible light. And so here's an example of something we call a planetary nebula. It looks like a planet because it's round. And by the way, the talk tonight at the Apollo Theater will be about these objects. These are called planetary nebulae, and they are the result usually of a star disintegrating. So when a star is old and becomes unstable, it's burned up all its fuel, or most of its fuel, and some of them send out puffs of material into space like this. So this particular one is particularly interesting for us because it has a strange spatial structure, and we can see the dust clouds that it's producing, and even calculate that there probably are five stars down there in the very center. So wonderful mysteries, and they're not planets, even though they're called that. So the third reason is to look at distant galaxies that are running away from us very fast, and we receive infrared light, which is light. It's like visible light, except the wavelength is longer. We see light that's been stretched on its way to our telescope. So the wavelength is longer. We need an infrared telescope to see light that was ultraviolet or short wavelengths. So that's what this little sketch is telling us. So what did we see? Here is an image of the sky, the first one that we released. And in a very short time, we were able to observe thousands and thousands of galaxies in this individual image. This is a little square of sky. It's about 2 arc minutes on a side, very tiny. Your eye has the ability to basically separate objects about this size from each other. The resolution is about 2 arc minutes or 1 arc minute if you have really good eyes. So in this tiny piece of sky, we have thousands and thousands of galaxies, those little specks and smudges. There are about 3 or 4 bright stars that are nearby, and those are the ones with the spikes sticking out. In the center is a collection of very bright fuzzy objects. Those are very massive galaxies. And around them are these little pink objects, this strange stretched curved ones. And those are magnified images of much more distant galaxies. So Einstein told us that gravity works by bending space-time, which means that gravity can be a lens. So it has the gravity of those big bright galaxies in the middle has bent and focused the light of the other galaxies and bent it quite a lot. Several arc minutes is not unusual, and the magnification can be 10 or 100 or even more on a whole galaxy. So we get basically our strategy now is find a natural lens that the universe has given us to use and study the galaxies that are behind that lens. So just a few things to show you. Here's a magnified image of a single galaxy, and you see it's been stretched out. They're actually a triple image of a single galaxy in this particular one. And we astronomers use it to determine the details, structure of that galaxy, as well as to figure out what the lens is doing. And this time there was even a supernova in that galaxy. You see the little dots that have circles around them. That's the 3 images of a single star, which is in the process of exploding and when it became old. So that's a remarkable story that we now have a new tool called gravitational lenses. A few other things to show you. This is the most distant galaxy we have found yet. We see it as it was when the universe was 290 million years old. So the galaxy was already there even before that. And how do you find them? You see that little sort of reddish smudge. So you have to take thousands and thousands of pictures of the sky and look for the very reddest objects. Then after you've found something that looks like it might be what you're after, then you spread out the light into a spectrum and see, does it have the characteristic shape that it would have if it's a very, very, very distant galaxy. So this is the record holder at the moment. So here's a pretty picture to show you. This is a place where stars are being born today inside a cloud of dust and gas. So people think space is empty. Well, not quite. There are clouds of dust and gas. And where does the dust come from? Well, the Big Bang only gave us hydrogen and helium, so there wasn't any dust in the early universe. There's the dust, and it is produced by those exploding stars that liberate the chemical elements that you see around you. So this is a place where stars are being born inside a cloud of dust. So why are they born inside there? Because it's cold inside. The dust protects the gas from the heat of the stars around it. The gas can cool off. Gravity can overcome the force of the gas and make something collapse and form a new star. So there are a few in here which you can barely recognize, little bright spots at the end of the towers. You can also see there's a wind blowing through space. And where does the wind come from? A previous generation of stars in the upper right-hand corner of the picture have let out a lot of energy, and they've been pushing and pushing and pushing the gaseous material around. So inside here, we think there are stars being born today with planets, possibly like the Sun. So here's another recent discovery from the Webb telescope. This is a spectrum, and this is an example of how we do chemistry onto this object. So a particular object emitted a burst of gamma rays, and we've able to find out where it was and point the Webb telescope at that object. And it has a spectrum which shows us that various chemical elements are included in the debris coming out. In this case, it says tellurium, tungsten, and selenium. They're all very heavy elements. So this is an example of how you get the heavy elements. So when you say, I've got a gold ring on, where did the gold come from? It could come from one of these stars that blew up. Also can come from when two neutron stars merge together, and that combination blows up. So that's pretty astonishing story. I'm wearing bits of a neutron star or bits of a star that blew up like this. And we know because of the Webb telescope. So here is a star that's being born with planets, probably. What you see right in the middle is a thing that looks like a hamburger seen edge on. And so that's like our solar system if you were looking at the edge of the solar system towards the sun. In this case, there's so much dust in that new solar system that you can't see the star directly. But you can see, but the light is able to get out, up and down. So we're seeing the light that's getting out. If you were to come back some other time, maybe the dust will have disappeared. It might take 100,000 years before the dust will go away. And you'd be able to see that there are planets in there. Now we're going to find out, certainly people are trying to see planets now, but it's kind of hard to tell just yet. So how do you know about planets around other stars? Well, this is one way. Planets go in front of their stars, and we've been watching this for a long time. We've discovered about 5,000 planets this way. So if the planet is large and the star is small, and the planet just is lined up so it goes in front of the star will blink for a little while and get a little fainter. And so this is how we found most of the planets that we know of. If you know about the star, you know how far away the star is, and you see how long it takes to for the planet to go around, you can calculate the temperature of the planet as well as the size from how much light is blocked. So now you say, okay, I know how big the planet is, how warm it is. Could it be like Earth? And then you say, well, that's interesting. Could it have an atmosphere? So the answer is, well, look and see. Does any light go through an atmosphere of that planet on its way to our telescope? And the answer is sometimes yes. So here's a spectrum that's been in the news recently. This is a spectrum of a very large hot planet. It's a combination of hydrogen, atmosphere, and an ocean. And the molecules, we spread the light into a spectrum again. The molecules that it's showing us are methane and carbon dioxide and a little bit of something called dimethyl sulfide. It's a not very complicated molecule, but it's something that we would not see here on Earth unless it would be made by living material. So This got a lot of people very excited because could this possibly be a sign of life elsewhere? And the answer certainly is not really. It's just proof that with technique is able to see interesting molecules. All the same, the public is excited about life, as they should be. So it's a hint. Maybe there's life elsewhere. And when we get better equipment, we might be able to tell you. So I just wanted to show you a few pictures of the outer solar system. Here are the great planets. They all have rings, by the way. The one around Jupiter you can't really see, but it has rings. Our infrared pictures are different from what we could get before. And I just want to show you a few things that we have discovered. Here is molecules on the surface of Io, or Io. Anyway, this is a satellite of Jupiter, which was discovered by Galileo himself in 1609. And it is very bright and very hot. It is hot because its orbit is not circular as it orbits Jupiter, and it's being squeezed and stretched by the tides. So it's so hot that it has sulfur volcanoes on the surface. And now we've been able to see there are molecules of sulfur dioxide on the surface. We are sending, Europe has just sent actually, a little satellite, a probe to examine the icy moons of Jupiter. The other three are icy, the ones that Galileo saw. So this is on its way out there to have a look. So why would we look at the other ones? Europa, in particular, is the second one out that Galileo saw. It has been visited by previous probes, and we know that it has an ocean covered with ice. And water comes spitting out from between the cracks in the ice blocks. And so we say, well, let's go find out if there is organic chemistry going on in that ocean. Could that be a sign of life? So this is a way that we have to hunt for life elsewhere. And now with the Webb telescope, we're able to say, and by the way, it has dry ice, carbon dioxide, solid ice on the surface of Europa. So it's definitely an interesting place to go look at. And the probe is on its way. NASA launched its own just to go look at this particular one. So where it is, you can't really tell what it's doing, but it's going to fly through the water that's coming out of the cracks between the ice blocks. We are also preparing a probe to go land on Titan. Many years ago, I guess it's maybe 50 years ago almost, we sent a probe called Cassini. It was mostly a European mission with United States participation. And we landed a little probe on the surface, it was called Huygens, because you can land on the surface of that satellite. This is because it has an atmosphere. This is the only big satellite in the solar system that has an atmosphere. It has enough that we'd be able to fly a helicopter. There's a little picture of it in the upper right corner that shows it's called an octocopter because it has 8 propellers. And it's almost 1,000 kilos of equipment. And it's going to go all the way out to through the solar system and land on Titan. So what are we doing with the Webb telescope? We're taking pictures and mapping the presence of different kinds of molecules to see what is the surface of Titan like. So Titan has a remarkable internal structure, and I think I have, on my next chart, I have a picture of that. No, maybe not. So the internal structure of this little satellite seems to have it's got an atmosphere of nitrogen mostly, with some ethane and methane. It's got lakes and rivers and clouds and weather of methane and ethane. It's got a surface of solid ice. Under that is probably what they call a clathrate of water with other molecules in it and organic chemicals. Under that could be an ocean. So quite possible there's a warm ocean under all of that. So it would not be impossible for this object also to be alive, and we can only know by going to visit and finding out. So that's coming, but it will land when it's going to launch. It doesn't say here, 2034, so we have about 9 years before we have any evidence about life on the surface of Titan or inside Titan. So everybody wants to know, how far can you go in the solar system? Can you go live on Mars? Well, yes, you could. Elon Musk says he wants to go. A lot of people want him to go. But this is a very dangerous and difficult trip. It's a very long trip. It's much, much, much farther away than the moon. And there's a fair possibility you would be sick when you got there, because cosmic rays pass through our bodies and damage us. Radiation illness is quite serious, and we don't actually have anybody that's ever been exposed to that much radiation on purpose. The astronauts that we have in space and in our space station, they're protected. The magnetic field of the Earth repels most of the cosmic rays. On the trip to Mars, they would not be protected, so they get a much higher dose of radiation. They may or may not feel good when they get there. So what can you do about this? Either you have to hurry, go very fast, or have to figure out a way to shield the astronauts with something like vast quantities of water. So maybe we can do this, maybe you can't. But anyway, we do have some of the equipment coming. If Elon Musk's starships actually work, then maybe they'll make it possible. So my thought on this one is, well, you could go, but you should learn how to reduce the risk. Something you should do first before you go is build a house. Build a house with a robot. We have robotic everything already here. Why can't we build a house on Mars with a robot? Either land a house or send some mining equipment and dig a hole in the ground so we can live underground, as I think we might need to do. So learn how to do that. Build a house. Make sure the food is there, plenty of oxygen, plenty of water, and then send the astronauts. But when you get there, it's still going to be an interesting challenge to be an astronaut, because you have to live in a very small box, about as big as a bus, maybe a minibus. Depends on how big your rocket is when you go. So this is a hugely difficult project to go live on Mars. And then when you get you there, we cannot bring you home. So it's going to be a one-way trip. And why is that? It's because you cannot carry enough rocket fuel to the surface of Mars to be able to lift off again. Okay, well, then if you really want to go and come home, you have to learn how to build a gigantic rocket fuel factory on the surface of Mars. So this is hard. So we should probably learn how to do it, but it's going to require chemistry, engineering, and some kind of fuel, some kind of energy source, either a huge solar array on the ground, or maybe even a nuclear reactor would be the first American, perhaps, nuclear reactor in space. By the way, the Soviet Union flew nuclear reactors many years ago, and a few of them have already fallen down on the ground, and that was bad. But at any rate, it's not impossible. It's just hard. So there's a lot to learn if you want to go to Mars. You should learn how to farm. I saw the movie, The Martian, and okay, now we can farm. No, you can't. You have to learn how to farm because it's all different there on Mars. It's cold, the atmospheric pressure is low, and you need a greenhouse. I see lots of greenhouses, but we're not ready yet. We have to do the details. Learn how to farm in lower gravity and lower pressure and lower temperature. Not impossible. There's a lot of science there. So basically, basic research is required before you're going to really like it. If you really want to make a civilization over there, well, you need to have a business plan where you're going to get paid. And some people think that's valuable, and people think tourists will pay, and I don't think so. So anyway, a hard project. Also, by the way, since you're going to live in a minibus, you have to be very friendly. People have done the experiment of what is it like to live in a small container with a few friends, and sometimes they are happy at the end, and sometimes they're not. They tried this in Arizona, and they had a fight. Anyway, so that's a hard project. Coming back towards the end of the talk here, what's the origin of life? Well, you have a choice of a few choices here. If life is really impossible, then obviously we don't exist. If maybe life is a miracle, life like ours is a miracle, and it only happened once, or maybe there are many. So there's the three obvious choices, and so we don't know which one we have. Scientifically, we have a way to find out. So my guess would be that it would happen wherever the conditions are right, with carbon, oxygen, nitrogen, and water, so that's not impossible. On the other hand, we don't know. How are you going to find out? You have to do research in the lab. See if you could make all the chemistry happen with the molecules that you think would happen naturally. So there's a lot of work on this going on, and there's a book by Jack Shostak and Mario Livio where they explain what they've done. So they conclude that RNA molecules are the secret, that most of the amino acids that make up RNA can be made by inorganic processes. That RNA itself is a big enough molecule to be a catalyst, so it can produce proteins and it can produce new RNA. So that's their idea, that RNA is sufficient to produce the beginnings of life. Now, where would it happen? They think it would be a lot like what Darwin said. Darwin said a little nice warm pond somewhere with water, but they think in addition it needs to have a way of concentrating the chemicals. So hot and cold, dry and wet. So you get surfaces that are coated with lots of interesting molecules, and maybe then spontaneously you might form cells from the certain fatty molecules and combining with other things. Not impossible. That's how it looks to them, but it's not proven. So who knows? Anyway, after that first gets started, then it's remarkable how long it's taken for us to appear. There's billions of years of life before there was much oxygen here, and then suddenly photosynthesis was developed, and then only about 550 million years ago, complex life occurred, and the cells learned to cooperate with each other to have predators and prey, for instance. When you have a big enough cell, it can eat another cell. So anyway, that gets to be pretty exciting. So general intelligence, well, this is a mystery. I don't really have anything to tell you that you haven't heard, but I would say it's not unlikely that we're going to have something, because I don't know of any law of nature against it, and people are spending incredible amounts of money and people time to develop it. So if it's not impossible, I think they're going to find it. I think you may not like the answer. I think it could be quite dangerous as a tool for malicious intent, as well as for great progress. So I don't know what we're going to do, but it'll be fun and interesting. So let me just talk a little bit about what happens next to us. In about 1 billion years, the sun will be too bright and it will be impossible for us to live here. In about 5 billion years, it will expand to be the size of the Earth's orbit, and that's pretty bad for Earth. Around that same time, the Andromeda Nebula is going to come and collide with our nebula, or with the Milky Way, and there will be some kind of collision. This particular picture I'm showing you is just a Photoshop version, so it's not an actual calculation. But there will be a collision, and stars will not hit each other very often, but the gaseous material between the stars will, and it will produce marvels of new generations of stars being born, and when that happens. So somebody else may find out about all this. Thank you. Questions? Do you have the possibility of questions?
Yes, if anybody's interested in asking a question, please raise your hand. We have some minutes for questions.
Wonderful talk, Professor Mather. Just a question, because you mentioned about primordial black holes, and I think primordial black holes are expected to have to evaporate also and to disintegrate and producing a short burst of gamma ray burst. So, as you know, sometimes there is a kilonova, which is a red object associated to some of these short events. So, do you think that Webb could be able to discover this kilonova associated to these primordial black holes?
Good question. So, question is the Webb telescope good for finding things that happen abruptly or suddenly, and not really, because we only look at a tiny fraction of the sky at one time. So if you tell us where one has occurred, then we can go look at it, but we can't find them ourselves very often. So probably no.
Are you already working on the next substitute to the James Webb telescope, and what new technology will it have?
I'm not currently working on that, but it would require a telescope at least as big as the Webb, but operating at visible wavelengths that you and I could see. It needs to be a much more perfect optical shape. And ideally, it would be a single perfect mirror. We can't. I don't know if we can do that. Because that would require an enormous rocket to launch a single perfect mirror, but it's not impossible. If you like Elon Musk, maybe we could use his rocket, because it's big. It would be big enough to lift a 6-meter mirror. So the special thing that it requires is called a coronagraph, which is capable of blocking the starlight without blocking the light of the planet. So the trouble we have to overcome is that the sun is 10 billion times as bright as the Earth. So that means you're trying to find like a firefly next to a searchlight, next to a lighthouse. So it's a very hard problem, and we know what we have to do, but we're not quite done it. Haven't quite achieved that yet. So it's not impossible. I should also mention I have a wild idea. The wild idea is if you could cast a shadow on the European Extremely Large Telescope by putting something in space 170,000 kilometers away and put it in the right place, you can cast a shadow of the star on the telescope without blocking the light of the planets. So it's called a hybrid observatory for Earth-like exoplanets, and I've been working on it for a while. And it's not possible yet, but it's not impossible either.
Sure you will get it.
Yeah. How about this idea that satellites are growing artificial satellites are growing so fast that it will be impossible to explore outside Earth anymore? Is there a solution?
Yeah, so there are some pretty interesting questions in your question. Number one is Starlink and its other communication satellites are so numerous that when we take a picture with a telescope on the ground, there's almost always going to be something, going through the picture. There'll be a streak across the picture. So it gets harder and harder to do that kind of astronomy from the ground. There's also a problem that eventually, especially low Earth orbit, there's so many objects orbiting they can crash into each other and make debris. And so then it becomes very dangerous to try to travel through with a new rocket or a new spaceship or even just a new observatory. It will be hit by debris. So we don't know what to do about that yet. People are thinking about it. International treaty, by the way, requires that you must be able to get rid of those objects. Thank you. We haven't. There are many thousands of objects up there already that are not under anybody's control. So, yeah. More questions?
Okay, thank you so much for your incredible conference. I'm only a mathematician, I'm not a physicist, but I have intuitions about time, space, and luck, because for me it's the same equation. And then, well, when we have a point has no dimension, so dimension don't exist. It's an idea. No? When we represent a point, it's a circle or something like it. You can see or you can touch. It's three-dimensional, at least, not zero. But this point, if you start moving in the time, you transform this point in two-dimensional or three-dimensional, 1 point. No? 1 point can be in a right line, 1 dimension, into dimension, or 1 point moves 3-dimensional. Only with time, 1 point in movement. And when with a line, well, you can move 2-dimensional in a plane, or you can move in a surface, 3-dimensional. And a surface, of course, if you move two-dimensional. And then T is for me more important than space, because if you introduce T in the equation, all is expanding. And all is T, as in the Lucy film, no? All is T for me. And then, at least last week we were watching Interstellar. I haven't seen go this. And I thought about love in the equation. The most important thing is not space, it's not time, it's love. And then I thought from last week to today that as the same way as a mother, a human mother, an animal mother, reproduce and love the generation, the children of the same way. I think universe in this point that zero dimension, no nothing. What's there here? What will be? If there was nothing, I think it was love concentric. I've always have thought that love concentric in a point, as God, I believe in God, expand as a mother reproduce and create the other things. And I wanted to know what you think about this intuition.
Yeah, good question. I think what you're talking about is something that doesn't exist in space and time. It's a phenomenon. Shakespeare doesn't exist as a physical thing either. All our stories, all our feelings, all our chemical processes, descriptions of things, relationships are not things that happen in space and time. So you're telling us about one very special one, love, but it's not in space-time. You cannot find it with science, I think.
Hi. So thank you very much for this very wonderful talk. I wanted to ask you actually two things. The first one was is about the composition of your teams. So you've spoken about chemistry, about physics, of course, biology. There's mathematics, all of them. So what's the actual composition of the teams that you're dealing with? I mean, you have engineers as well. So, yeah.
Okay. So that's a large question. We've detected that quantum mechanics describes all the waves in quantum mechanics, beginning with the inflation field, and then the nucleons, the quasar, and gluons, and all the other things that hold things together. So what we see in our world is all composite. It's made out of the tiniest wavicles, and now we work out the processes in which they interact. So everything in chemistry, everything in biology is all quantum mechanics. So but if you're asking something more fundamental, I don't really know a more fundamental answer to that.
No, actually, it's more practical. It's in your team, in the team that you lead. I mean, when you in one of these very big projects, there are physicists, there are people who are physicists, who are chemists, who are mathematicians. Yeah, the actual composition.
Okay, who does it take to make a project like this? It takes every kind of scientist. We need astronomers to say this is why it's important to observe. We need computer scientists to give us the tools to control the observatory and also to design the equipment. When we say, I need it to be this big, I need somebody who knows about materials. And the mirrors are made of beryllium, for instance. Beryllium is a special material chemically. Also, it's produced by a special metallurgical process. Then we need to have someone who knows how to polish the material, so there's optical scientists. And basically, every kind of person is required in a project this big. 20,000 people includes secretaries, lawyers, accountants, contract specialists, engineers, scientists, managers of all flavors. So basically, if you wanted to work in a space business, whatever it is that you like to do, we need it.
Great. And then a physical question is about dark energy. What's your view of the current status of what's going on with dark energy?
So what's going on with dark energy? We're pretty sure it's doing something. It's making, that's the name we give to the fact that the universe is expanding faster and faster all the time. We don't know if it's a constant, as Einstein suggested, or if it's a variable. And if it is a variable, then what would you do about that? So right now we're trying to get data. So the European mission for this is called Euclid. It's already been launched. In a couple of years, NASA would launch a mission called the Nancy Grace Roman Space Telescope. We'll do it a different way. Both are done by measuring what are the galaxies doing. So we'll have more information for you in a few more years. I don't think they're going to tell you what it is, it's going to tell you what it does. To tell you what it is, we are missing something complete. And when we tell you that we have a standard model of particle physics, it never predicted that. So, and it's very hard to produce it in any of the theories we have. It's one of the worst predictions in history.
Thank you for a wonderful talk. I wanted to ask what are your thoughts about Planet 9? And if you think space instrumentation can help with this and how?
Planet 9, okay. Planet 9, well, we used to have Planet 9. It was called Pluto. We demoted Pluto, said it was a dwarf planet, but it's still there. They don't have it doesn't have any opinion about this, I think, but Planet 9 is a prediction based on the orbits of other objects in the outer solar system that says there's a massive object, quite a lot more massive than the Earth, that's been affecting the orbits of clouds of small objects way out there. And this prediction was made quite a few years ago, and people started looking, and we have not found it. So Webb telescope is not a good tool for it because we only see a tiny amount of sky at one time. But if somebody tells us where it is, we can study it, and it would be quite a fascinating target. So ask again later.
So would you accept the proposal with, would you accept observation proposal with known coordinates, with suggested coordinates?
Well, if someone told us where it was, we would surely want to look at it. Right now we don't know where it is.
Perfect. No.
Good afternoon, Professor. I want to ask you if you think that SpaceX will replace NASA as a distribution in the future.
So I couldn't really hear the whole question, but it was about SpaceX.
Yeah, SpaceX.
Yes, so SpaceX is a rocket company.
If NASA will be replaced by SpaceX in the future?
Actually, no. NASA does things that SpaceX doesn't do at all. SpaceX is a business, and their job is to make money. So they sell rockets to NASA and other people. They sell communications services with Starlink, and they, up until now, they've not done any astronomy or research of any sort that wasn't necessary for their rockets. So it's a completely different subject.
Okay, thank you, John. I guess that the question is if you believe that we'll be able to contact with now neighbor in the future, or we soon do share the contact with us.
So asking about other civilizations. So if we knew how to talk to them, we could talk to them now. If we knew there was somebody on the other side of the galaxy with a receiver and they were waiting for us to send them a message in a certain way, they would be able to get it. But we don't. So we can only guess where to send information or where to listen. So I think we're not going to find it. I think we should keep on trying to find it, but I don't think we're going to find it. So how likely is it? Well, astronomers are working on how many planets could support life. We might even find out how many planets do have life. But then the last question is, well, how many planets want to talk to us? That's a harder problem. By the way, we can't go there in person. It's way too hard. It takes too long. Even at the speed of light, it would take you 4 years to get to the nearest other star, and you can't.
Okay, so we have room for 2 more questions, and then we're done. Okay.
Hi, thank you very much. What is the latest theory on what happened to the dinosaurs? Was it a meteor? And is that a possible threat to our extinction before 4.5 billion years?
Yes, so well, we definitely know that a meteor hit the Yucatan in Mexico, and a huge disaster occurred. In fact, I've actually touched the skin of a dinosaur fossil that was killed on that day. They found it in I think North Dakota, and they found out how the water moved back and forth, and so anyway, we know that was a very bad day for dinosaurs. It might be that a few of the dinosaurs, of course, survived. As you know, chickens are descendants of dinosaurs, but all the other big ones died. Mammals survived, so yes, we are at risk of future ones, but that was 65 million years ago, so chances are it might be another 65 million before another one like that comes. In the short term, there are a lot of smaller ones that are also dangerous. There was one over in Chelyabinsk not so many years ago, and some people were killed. And if this happens to you, don't run up to the window glass. They were killed by the shock wave, which broke the glass windows and hurt them. It would have been okay if they weren't standing by the window. So we have the job of finding those as much as we can, but those are small. So we more or less know what to do if we find a big one, but probably they won't be coming anytime soon.
And all further mysteries you've talked about here, do you think any of them could be solved by the end of the century?
Well, I don't know how long it takes to solve these mysteries, but some of them might be solved by your students. Some of them are in reach of modern ideas and modern approaches to science, and some of them may be impossible. So, I think please encourage your students, and if you're a student, please continue to study sciences, because there are breakthroughs to be found every day.
Okay, thank you. I think if there's no any other question, this is the moment to thank Professor Mather with a big applause.
Thank you for your wonderful hospitality. It's great to be here with you.